All right, so now we're ready to talk about the sum of geometric series. And these are some interesting things to talk about. There's going to be two different formulas that we have to consider. The first one would be if you had a finite geometric series and we wanted to know what it all summed up to. The formula would be S sub n equals a sub 1 times 1 minus r to the n over 1 minus r. Now, the interesting part comes into play when we talk about infinite geometric series. So let's take a step back here and think about how unusual this might initially seem. We have infinitely many terms, and we're talking about adding them up and coming up with a number. And that does work under the right conditions. Now, the conditions stem from the formula being the sum equals a sub 1 over 1 minus r when the absolute value of the ratio is less than 1. So when the absolute value of the ratio is less than 1, then the infinite series, the infinite geometric series, can sum to this guy right here. Okay? Now, we'll start with the proof for the finite, and then we'll talk about why, under these conditions, the infinite geometric series can actually converge to a number. All right, so now to prove this, you can see that I have a finite series, and you can also see that there is a common ratio. For example, if I just take these two and I divide, I'll end up with a common ratio of r. If I take these two and I divide, I'll end up with a common ratio of r. So this has been constructed so that it's a finite geometric series. So now I'll go ahead and to kind of get this thing rolling, I'm going to multiply the whole thing by a negative r. Okay, so I'm going to take a negative r times the whole thing, times both sides. And as I do this now, I want to be clear that I'm doing exactly something that's legal. I'm just going to shift things down. For example, if I take this guy right here and I multiply it by a negative r, it's going to give me a negative a sub 1 times r. So I'm going to write that right here to keep things neat. If I take this guy and I multiply it by a negative r, it's going to give me a negative a sub 1 r squared. And I'm going to write that right here. Negative a sub 1 r squared. So you can probably see the pattern already. And if I go out far enough, and if I multiply this guy right here by a negative r, that's going to give me a negative a sub 1 r to the n. Okay? So if I go out far enough, that's going to give me a negative a sub 1 r to the n, which means that the previous term right here would actually be an a sub 1 r to the n minus 1. Okay? So at this point now, I'll go ahead and I'll add both of those things together. And because of how I shifted things over a little bit, you can probably see that a whole lot of stuff goes away pretty quickly. So then on the left side, I'm going to have S sub n minus r times S sub n. And on the right, I'll have an a sub 1 minus an a sub 1 r to the n. Now, on the left, I can factor that S sub n out. And on the right, I can factor the a sub 1 out. And to get the S sub n all by itself, I'll divide by 1 minus r, and we can see the S sub n equals a sub 1 times 1 minus r to the n over 1 minus r. And that's the formula we started with. Okay, so that one's taken care of. Now, the second part here, it says for infinite geometric series, why must the absolute value of r be less than 1? All right, so now what we're thinking about here is we're thinking about this n going off to positive infinity. That n going off to positive infinity there. So let's think about this for a second. the absolute value of r needs to be less than 1, which says the same thing as -1 is less than r is less than 1. So if we think about numbers of r that are between -1 and 1, what we're thinking about are proper fractions. Proper fractions are where you have a smaller number on top and a larger number on bottom. Things like 2/7, things like -3/8, stuff like that. And so when we talk about n being infinitely large, then what we're really talking about is this bigger part on bottom dominating the small part on top. So let me show you here. If I go ahead, and this is going to be some pretty loose notation, but I think it'll be enough for you to get the idea. If I have 1 minus this fraction here, this proper fraction where we have a small number over a big number, and this is an infinity up here, okay? Well, when we look at something small over something big raised to the infinite power, then the bottom, the big part on the bottom here is going to dominate, and it's going to push us off close to 0. So at infinity, this whole piece right here goes off to 0. Now, we've studied limits a little bit, and this is a limit discussion. Now, I'm not going to go into great detail, but know that whenever we talk infinities like this, we have to talk limits. And so the limit of that part would take that individual part off to 0, leaving us with just the a sub 1 over 1 minus r. So again, that's the n going to infinity. That's the number of terms going to positive infinity, showing us that when we have a proper fraction as a ratio, that whole part goes off to 0 and is negligible in the entire formula. Okay, so now we're ready to use these formulas. And in the first example, we're at I equals 0 to 30, and you can see that the function that's sitting out here, this is an exponential function. So we know without having to do a whole lot of work that this is going to be a geometric series. Now, if you didn't see that, if you forgot that, you could always write out the first few terms and then see if there's that common ratio. But it'll sure save you a lot of time if you're able to recognize that that's exponential. Okay, so we've got a finite. Notice it ends at 30, it looks like. We've got a finite geometric, which means that we'll need to use the formula a sub 1 minus r to the n over 1 minus r. The first term, a sub 1, can be found by taking the 0 and plugging it into the I. So a sub 1 gives us 300. The r is the ratio, and from the formula earlier, that base of the exponential is always going to be the ratio. So for us, the ratio is negative 1.08. And then finally, the n would be the number of terms. We start at 0, we end at 30, so there's going to be 31 terms. Taking all of that and plugging it in, the sum of the 31 terms would equal 300 times 1 minus negative 1.08 raised to the 31st over 1 minus a negative 1.08. You will want to be very careful with your parentheses right here because that negative raised to the 31st power is going to keep it negative. So that's going to end up being a 1 plus whatever 1.08 to the 31st power is. So be careful with those parentheses there. And then when you add all this stuff up, this is clearly a calculator problem. You get 1711.68. So we say that this series converges to 1711.68. Okay? Now, the next example that you see in the notes is 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16. That plus ... there at the end implies we're dealing with an infinite series. The only way that we can sum this up and to get it to converge would be for the absolute value of the ratio to be less than 1, and meaning it's geometric as well. And so if you look going from right to left, it looks like all of the ratios are 1/2. So it's an infinite geometric series. The absolute value of the ratio is less than 1/2, which means that this sums up, this converges. The formula that we came up with a moment ago was that. So the first term being 1, the ratio being 1/2, tells us that this thing converges or sums up to 2. So pretty easy to use the formula, but I also do want to take you back to look at the example. Remember a few minutes ago I said that we had that small over that big, and at infinity that went off to 0. Here with a concrete example, it might be a little bit easier to see. You can see that if I continued on here and I had a 1 over 32, a 1 over 64, a 1 over 128, all the way to wherever, then these numbers are getting closer and closer to 0 as I move out to that positive infinity. So at some point, they're inconsequential to the overall sum. They're so small that it's not affecting what it actually converges to. Okay? The last thing I'll say is that if you decide or if you find out the absolute value of the ratio is not less than 1, then the series would not converge, but instead we say that it diverges. So if we can't come up with the sum, if we can't say that it converges, then it has to diverge.